That always happens. My name is Jan Peters and I'm going to talk to you about our research on teaching robots new tricks using machine learning algorithms. And maybe before I start, let me start with a video. This kind of video is what brought many of us into computer science, right? You saw in there robots doing pretty fancy things. And for me, this is obviously very, very close to my heart. I did my PhD about 8 miles away from Hollywood. So really around the corner where that movie was made. Now let's have a look at reality. And actually a very weird reality, because to realize Hollywood dreams, maybe you should look at a robotics commercial. Let's have a look at the commercial from the 1960s. In the 1960s, the company Unimate had just made the first robot. And this first robot, they were so cocky, they thought in the 1960s they would bring this robot right soon to Earth, some form of this robot soon to our homes. Now you will see the robot in a moment and you'll realize that, well, that is a little bit too big and clumsy for our homes. So that's clearly not the robot which we will see in our homes. But this is actually the first industrial robot. And when you look at most robots to date, they've actually not changed so much. When you look at the social surroundings of that home, well, that social surroundings has changed totally, right? I mean, the housewife is luckily in most countries kind of a history, and well, and the robot, well, most of the situation there is fairly, well, not fairly anachronistic to current days. But if you wanted to program these robots, you would do it today exactly the same way as people would have done it in the 60s. There's very, very little progress we have actually made in programming robots. And the big problem behind this is that, so soon you will see the only scene which was faked in this video, since that can't open the champagne bottle. But you basically see how good human programming can be. If you also realize people in the 60s were capable of programming this, so quite obviously, if you know further today, this means we've really failed in classical robotics. Since just programming the robot, that cannot be the future. So instead of, if you really want to realize Hollywood's dreams, it can't be that we take smart grad students, put them in a center, give them pizza and Coca-Cola, and have them program all the tasks of the world, but really that we have to have the robot learn all of these tasks pretty much by itself. And that is what my talk today is about. Let me just quickly close this video. So, we're far from having this robot at home, and the programming obviously is the key bottleneck. It's not the robots. So, why don't we have such robots? Well, quite simply, there's too many tasks, the tasks contain too much variability, and there is way too much uncertainty in the real world as that we can realize it. So, let's have a look. What actually made the Hollywood movie difficult? Well, when you have a look here on these sites, what you directly recognize, there's a hell of a lot of uncertainty in the tasks and in the environment. Taking out these dogs would actually be a challenging task, whether it's for a humanoid robot or even just a mobile trash can. It would be really hard. Adapting to humans and interaction is quite a crucial thing. I would not recommend that you bring your child anywhere close to a humanoid robot at the moment, unless the child has been perfectly laser scanned, as the humanoid would probably be a bone-crushing hug for the child. And finally, well, when you look here, you recognize that the programming complexity of such a scenario is way beyond human imagination. So how can we fulfill Hollywood's vision of future robots? Well, it can't be smart humans. Smart humans we've been doing for 50 years, and we have gotten no further since the commercial I showed to you in the beginning. Well, just learning off-the-shelf methods will also not suffice us, simply because we'll never have enough data in order to train the robot for all the tasks which we have. So what we really need are task-appropriate learning methods that can map robot sensing to actions. So what happened here. So, so basically, what I want to show you today is our journey through a learning system, which obviously is a teacher, but particularly creates its own data through its own actions, and by that always changes the state. Let me start before in order to get into there, with an introduction, and then I'm going to address the core questions of the talk, which is what are suitable, how can we develop suitable learning methods, how can we learn elementary behaviors, how can we compose more complex behaviors, and how can we adapt to humans in interaction. And finally, we're going to show an outlook and a conclusion. So let's start with an example. This here is actually the only intelligent robot we know. It's a human, and this human has a table tennis racket with a ball on a string. And it obviously sees the ball, so it has an internal state, which is the arm state, and it has an external state, which is the ball state. In addition, it has to generate actions, which are in this case just muscle commands. And what we would like to learn here is we would like to learn a mapping from the state to the action. So that such kind of mappings, they are usually called policies, and they tell us what action to take in one particular state. Then we have the teacher, and the teacher generically, in our case, gives us a feedback in terms of a reward or an error, and we usually just call this a rating or reward. And finally, the environment, of course, changes, since every time we take an action, we change to a different state, and by that we get a different scenario. Classically, people in engineering try to write down functions of the world. These functions were supposed to be really complete and tell us exactly what next state comes for every state action pair. But in reality, our world is uncertain. And the only way of how we can even phrase this world is using probability distributions, such as a distribution here over the next states, given the current state and the current action. That's a basic model. And of course, we're not just interested in one state, in one action. Oh, sorry, but in a full series of them. But let's first focus on this policy, this idea of how can we map states to actions. And for that, we realized that we want to model a behavior. Well, ideally, we would like to have a set of rules. In classical artificial intelligence, in the 1970s, in the 1980s, they actually tried to come up with one set of rules to describe intelligent behavior and the intelligent mind, and they completely failed. We all know the reasons, like that you can't figure out a rule, what is a bird, because, well, if you make the rule birds are animals that can fly, and then you suddenly see a penguin, which is still a bird, you clearly realize that rules usually fail. Then machine learning said that, well, you should probably not engineer this, but you should learn a deterministic function, a deterministic mapping from state to action. Now that, surprisingly, still fails. And there's one very obvious part. If you try the same thing over and over again, of course you will not get new data, and you will not try out new actions, and you will not learn. So what you really do need is stochasticity. You need stochasticity for exploration, for trying out new things. But it even eases algorithm design. So many of you may remember from your early computer science lectures, the very first lectures about sorting algorithms, where you learned about first double sort, which was really bad, and then you learned about quicksort, and you realized that there was very little difference between the two. Just that there was this bit of stochasticity in quicksort, which made all the difference to bring down the complexity. And what's actually pretty amazing is that there are quite a few of... Oh, when did you lose me? Just now? Okay, yeah, there's a network error. Fantastic. We are having... Okay, I guess I'm cursed today. So, and then there are things like that you know that there are quite a few problems with it. We know that you need exponential time in order to get a deterministic solution, but the stochastic solution can probably be gotten just in linear times, like estimating the volume of a polyhedron. And finally, optimal solutions in problems where you don't observe full information are quite frequently stochastic. So if you have an optimal control problem and you don't know everything about your environment, it can be that the optimal solution is stochastic. And finally, when you look at me, you recognize that my hand's a little bit trembling. That's actually fairly normal. We have a tremor, and this tremor for humans is functional. It actually helps us explore, and it can be a smart idea to model the variance of the teacher. So, with other words, we may want to learn a stochastic used for learning. Now, of course, we're not just interested in one state and one action, but we're interested in a whole series of them. And what we get from them are then trajectories, which consist of states and actions. And using the assumptions from before, we can write down path distributions and the accumulated path rewards of the teacher. And, well, what would be learning? Well, I'll show you an example from one of my students. He created this little robot, and he wanted to teach it to walk. And he first tried really, really hard to code the behaviors by hand. And what you see there are the initial behaviors which he coded by hand and brought into a stochastic policy. And you recognize they're not very good, but after optimizing this policy by learning, well, you see here that it actually gets up to an average velocity of about ½ meter per second, and it can actually do pretty long distances. So how did he accomplish this? Well, he accomplished it by basically saying that you want to maximize the expected return, the expected scores of the teacher, and that you would explore the parameter space in order to do this. And in return, get to the next state with environment. So now I can finally focus on actual questions. But our first question is, how can we actually find suitable machine learning methods? And as you may have noticed this, if you were starting your life trying out everything by yourself, you would probably never leave primary school. In fact, you may never leave kindergarten, because your world has so many things to try. If you were trying all of them, this would be really, really hard. So the key thing which we humans are primed with is that we have quite a few core reflexes. Some are just for keeping us alive, like breathing, like the heartbeat reflex. But others are really built in to guide us towards learning. And one of the strongest reflexes you have right when you're born, that's the reflex to imitate. You can show a child just being 1 hour old, you can make faces to it, and it will start imitating the faces. And they're pretty crazy. It's pretty crazy how fast we're primed to imitate. And hence, well, that's obviously how we should always start a robot learning. So initially, we want to acquire policy from the demonstration. The teacher provides demonstrations, and the student just tries to reproduce this behavior of the teacher with his own distribution over the past. Just like that tennis student is doing it with a table tennis teacher. So, intuitively, what does this mean? Well, it obviously means that we're asking the question of whether, if we have a path distribution, can we reproduce the policy? And it turns out that if you have a distance measure between distributions, F measure, which just shows the discrepancy between two distributions, and we would then have here intuitively just the actions, the states, these were the samples we would see, well, then we would try to reproduce this yellow Gaussian distribution. What's interesting, of course, is if we choose a good F measure, like let's say the logarithm, this just becomes the KL divergence, and we can actually derive supervised learning algorithms for it. And in fact, it just becomes minimizing the distance between the distribution which we generate and the distribution which we have observed from the teacher. So we can do this, luckily, just by adapting the policy parameters. And if there is one robot has learned basically to throw the ball always in such a way that the other guy can catch it very reliably. So I hope this has made the case to you that we have figured out how to learn elementary behaviors quite well. Only very few primitives left. Here you see a game, what we're going to do next, or what we're planning next. We want to invite people to play tetherball with the robots, but it's in our lab, and have people submit their own learning player. What's actually kind of cool is this handcrafted player was done by 8 master students who have worked 1 year really hard on it. While the learn player was done by 1 PhD student who worked 1 afternoon on it. So you recognize how powerful learning can be. Okay, I will skip a few things. We obviously want to apply this for many things, including manipulation, and here you see different results from manipulation, like stacking blocks to get the highest possible power. Then this here is a long sequence for cutting an eggplant, and with a knife, well, the robot has to perform quite a big series of primitives. Up there you see how the robot is actually doing a pepper mill task, and all of these can be learned by a mixture of demonstrations and reinforcement learning. So, finally, I want to get to one more question, and I hope I still have the time, since I have no clue when I should have started and ended now, given the current, all the mishaps. But if you are staying with me for one more big question, then I'll show you a little bit of what we have learned about learning to adapt to humans and their interactions. And let's for that quickly return once back to table tennis. Now, you've noticed that the robot table tennis player there wasn't very good if you compare it to like your little sibling who's been playing in the schoolyard, or your child playing on the schoolyard. And some of the reasons are pretty obvious. Imagine you were nailed to the ceiling playing table tennis. It's pretty hard to be nailed to the ceiling and play just with the arm table tennis, because it would be very non-linear behavior. Yeah. So the workspace is quite limited. The second thing is somewhat counterintuitive, but while our robots are faster and more precise than humans, they actually are not that good at accelerating. Human muscles are fantastic actuators, enabling much faster acceleration. And by that, they have something which we still don't have in robotics on the pure hardware level. And then there's a third problem, and the third problem confused us, since the robot had a pretty bad reaction time. It turned out that this was mainly due to the fact that spin really only becomes predictable once the ball has gone up again from the table. Once it has touched the table, it becomes predictable. Now the first two problems are hardware problems. And yes, you can solve it probably by adding a robot onto a floating base and giving it muscle-based actuation. But this is mainly really a hardware problem. But the third problem, the reaction time problem, is actually a problem which we see in humans too, since this year there's a baseball task, and this is the last moment where this human baseball batter is producing any output based on the visual stimulus of the ball. And when you think about this, let's quickly go back to give you a good feeling. This here is about, 10 to 15 meters, and the ball is about as big as my hand. The racket is about as thick as my arm, and just based on prediction, the human is nevertheless capable of reacting to the ball and managing to hit it back. Now, quite clearly, this cannot be the amazing accuracy of the human predicting the ball trajectory, and it also is not. since what we have learned subsequently by talking to table tennis players, professional table tennis players, is that humans are actually trained not to look at the ball, but they're trained to look at the opponent. So, with other words, they do opponent prediction. And that's exactly what we ended up doing, since my PhD student Ji-Kun Wang, a former PhD student, is now at Google, and this here's the ball 320 milliseconds before he hits it, 180 milliseconds before he hits it, 60 milliseconds before he hits the ball. And what he creates is a predicted distribution where, in this case Jigo himself, but the human player will shoot the ball to the opponent court of the robot before the human has even touched the ball. And the amazing part is, you can actually predict this with an accuracy of about 35 centimeters. There's already 320 milliseconds before the human has touched the ball. And it gets even more accurate the closer, of course, the ball is to the racket, and after the human has touched it as well. Now this has allowed us to do something really, really cool. So in this case, we just gave the robot 3 primitives, and a forehand, a backhand, and a middle strike. And we have allowed the robot to use these primitives and to simply return the balls to the human completely based just on both professional players. This guy here actually is a European Champion League player, as well as laymen can play table tennis. And for that we recover the reward function of the humans. And this is, for example, a pretty good area for this guy, because that guy will have to do a backhand and jump onto the table in order to get it. This here is a pretty bad area for that guy, simply because, he cannot really execute it that well. While these here are easy to take for this guy, so they're also bad for our player. And it turns out that after we have looked at about 300 features, we actually saw that the key features are things like distance to the table, movement direction of the opponent, distance to the opponent, velocity of the ball, angle of the incoming ball, whether it's a smash or not, and the opponent elbow. And that the most relevant of these features, that these are just the most relevant of these features, explain the reward function of the student. What's really interesting though is, when you look at what actually makes the expert, but the really great player, different from the European champion level player, different from the layman player, then you see it's the table preferences and the angle of the incoming ball. And to us, this indicates that actually the fantastic expert doesn't have much better strategy. He just knows he can play better, and he will use features stronger, which the other person, the layman person, could never use. Alright, finishing up, interaction primitives are another scenario which Heini Benamura, one of my former postdocs, worked on, who basically took our scenario and then used it in order to do human-robot interaction, like in this high five task, where we would infer all the tasks where we learn from 2 humans, where we have a known and an unknown agent. We would learn from 2 humans, then basically create a predictive distribution over the primitives, and once we have observed part of a human primitive, we can then turn on a robot, according to a robot primitive, simply by prediction. And both Heini and my PhD student Marco managed to learn tasks like this handover task where they assemble a box together simply by interaction. The robot always predicts what the human needs. Unfortunately, we don't have a feeder on this one. But on the future, some newer videos, we actually have a feeder where the robot automatically gets all the screws and so on. Part of the team which all contributed to this.
Okay, so thanks to the speaker. We have time for 2 or 3 questions.
Thank you for your excellent presentation. So I have a few questions. My first question is, do you agree that what you have presented, the system of the teacher, the robot action, is like a multi-agent system?
So we've looked, at the moment, most of the cases we have only one agent, right?
Yes.
It's only for the throwing and catching we have 2 agents, and for the interaction stuff we also have 2 agents. One of our goals, which my colleague Gerhard Neumann, who is pursuing together with 2 students in my institute, is actually to bring such things to multi-agents. And that's one of for that we have the kilobots, which are like tiny robots. We have about 100 of them, so not a kilo, but just 100, so centi. And they try to do assembly tasks together, and that's one of the tasks which we have there.
Okay. And do you focus on cooperative behaviors or competitive behaviors? Because here we have learning, so for me it's cooperative because we want to improve the robot. But when the robot he has to compete with a real human player, so
we've looked at both cases. We've done more work on cooperative scenarios, since in the end these have more wide applications than competitive scenarios. In table tennis, obviously competitive is interesting, but for example for manipulation in industry, the cooperative scenario is the only one which is interesting. And but yeah, that's why we've focused more on the cooperative, but we've done also quite a bit of competitive.
And I want to talk about about the psychological part. I mean, do you focus on making perfect robots, or do you want to integrate, feelings? And for example, when the robot plays well, he is confident, and this kind of feelings. Do you work on this?
Okay, so I don't know what I would call being confident a feeling. I mean, for humans, we can mistake this as being a feeling, but that's one of the few. Most of the things we consider feelings, we have no clue how to quantify them at a mathematical level. But being confident is one of the few things we can quantify, right? If your system becomes very certain about doing the right actions, and that happens actually automatically for our systems. I showed you in the beginning that our policy is a distribution of the actions given the states. And in the moment where this becomes closer and closer to Dirac impulse, so closer and closer to certainty, and the variance shrinks, well, that's obviously the moment where the system becomes very, very confident. And that's actually a key feature for us, because that means our behavior is converging. And one of the biggest problems we actually have in many algorithms is that you have premature convergence, where the algorithm gets too confident too fast. And then you actually need to slow it down and regularize for that.
Thank you.
I have one question. Today in games, using reinforcement learning, we can beat the world champions.
Yes.
To what time you can imagine that using robots we can beat the world champion in tennis, for instance?
Well,
can you imagine that in the future?
So I think that there's 2 components to it. One is the software component, and actually there I really have to add that playing games which are discrete, like Atari games, where in the end the actions are discrete. You can search the action space. Where searching the action space is still a cheap action, a cheap operation. We are far from that in robotics, because searching the action space is not a cheap operation. It's one of the reasons why parameterized policies are preferred versus argmax policies. So I think there is a factor of, I don't know, maybe 100 already just from a substantial factor in complexity between continuous state action problems and discrete action problems. And that's something we should not underestimate. So that's on the learning algorithm side, where we have a huge problem. The other problem, though, is that we also have a robotics problem. Since in order to make learning algorithms work on robots, you have to make them real time. You have to make them work with little data. You have to make them work with very noisy sensing. And you can't run millions of trials in order to figure out what works and what doesn't work. That makes robot learning substantially different from machine learning. And then you have a pure hardware problem. The pure hardware problem is, well, imagine you were nailed to the ceiling playing table tennis. I'm pretty sure my robot would actually be able to compete against you being nailed to the ceiling. But I don't want to nail you to the ceiling, don't get me wrong. But in the foreseeable future. But a human can sidestep. And by sidestepping, we can use the same primitives many times. And so that gives us a significant edge. So we would need hardware comparable to humans, or better than humans maybe. And there's very, very few areas where robot hardware is generally better than humans. So that's actually one big problem for robotics.
In practice, do you have some real applications of those technologies?
Yes, we're working with quite a few companies where we bring this into industrial manufacturing, and our hope is to basically make it possible to make more products producible by robots and fewer need to be produced by humans. One hope for us is, of course, also that in the future we have we can maybe even learn the skill of a very good surgeon and transfer it to a machine so that it can be used by way more machines than we would have surgeons being able to perform the operation. But that's a future thing, of course, that we haven't worked on. We've worked on rehabilitation, where it can actually be very useful, since there's always a lack of nurses in rehabilitation, and I think that's a very promising area.
So for more questions, I suggest in the coffee breaks because we are too late. So thanks again for the speaker. If you have some.
No, just for the coffee break, that's only 10 minutes. We must start.
Okay, so it will be very quick.
Le logo.
Ma facciamo ricordare che siete sereni.
Von der Hälfte?
Sehr